Hello, Chem 2, and welcome to the technically part one of the last sections of chapter 2. We're going to cover sections 6 and 7, and I'm going to break this into two videos because this is a lot of content. It's all about formula writing and naming, so let's get started. So you can see for the objectives down here, it says predict the formula of the ionic compounds from charge ions and write formulas and naming acids. So it's a lot of naming, formula writing for both ionic, covalent, and acids. We're going to focus mostly on this video on ionic only. So let's get started. It is chapter 2. Again, the last thing is all about naming compounds. We're going to do the formulas first. So section 6 is all about formulas. Section 6 is all about formulas. Section 7 is all about the naming. It's all blended together here as part of the first section. So we're going to focus predominantly on ionic bonding. Ionic bonding involves a transfer of electrons, which means very simply that one atom has some loose electrons, another atom needs those electrons. So the one atom that has loose electrons will lose electrons and will give them to the other atom. In general, metals have loose electrons. That's actually what makes them conduct electricity, because those electrons can freely move, but they are so loose that they can be transferred. If a non-metal who really likes to grab electrons comes along, that non-metal can grab the electron and as a result make the metal have a positive charge of some quantity and can have the non-metal have a charge of an equal quantity. So how does this work? So what has to happen when you're doing this is you can't just have electrons disappear or have electrons just appear. Whatever electrons that are lost by all of the atoms of the metals have to be gained by all of the atoms of the nonmetals. So we're going to have what's called electrical neutrality. The total number of electrons lost and the total number of electrons gained are going to be the same. So in general, if I look at the periodic table, I can see that there's trends associated with the periodic table. The trends are that your atoms that are far to the left side, those are going to form plus charges. But if you think about it, that first column has only one extra electron over a full shell. So it will readily lose that one electron to become full. And remember from Chem 1, you talked about the octet rule and all about trying to, whatever it takes in order to get up to a full set of 8. Column 2 will lose 2. Column 17, the next to the last column, will gain 1. And column 16, which is right next to that, will gain 2. So there's a definite patterns associated with the atoms on the periodic table. Metals closer to the noble gases, remember the periodic table is the cyclic nature, they're going to very easily form positive ions. Now, the things in the middle, the columns 3 through 12, they act really, really oddly. They are metals, so they will lose electrons, but they have a variability of the number of electrons lost. They are what the term is referred to as multivalent. They have multiple charges they could possibly form. So, for instance, I show you down here that iron can form very readily form a +2 or a +3. Iron is in the middle. If I were to look at a periodic table, and if you had me for Chem 1, you would have colored a periodic table that looked a lot like this. And actually, to help you out a little bit, if you want to print out this slide off the PowerPoint that's going to be provided, this would be a good one to print off. Notice that column 1 forms only +1s, column 2 forms only +2, column 3, way over here, or column 13, 3A or 13, forms only +3. And then everything else, with a few exceptions, are multivalent, means they have various or multiple possible charges that they could form. However, on the non-metal side, it's a lot more structured. Column 17, now notice hydrogen there. Hydrogen acts really weird. Hydrogen can act like a metal or a non-metal. They all form -1s. Oxygen family forms -2. The nitrogen family forms -3. And carbon, in the rare exception when it does form a ionic bond, it forms a -4. Notice that there's no variability over here. There's only variability on the metal side. So how do we go about writing a formula? Well, it's actually kind of simple. you're going to write the symbol and the charge of the cation. Then you're going to write the symbol and the charge of the anion. And then you're going to balance the number of pluses and minuses using what's commonly referred to as the crisscross method, where I extended to be crisscross and simplify. Now, here's a list of, they talk about these polyatomic ions. Polyatomic ions are special ions. If you look at this chart here, these are all monoatomics, a single atom that can form a charge. But you also have the possibility, if you remember from Chem 1, that if you combine atoms together, they might have a total number of atoms that are covalently bonded together, but then they're going to have an overall charge. So for instance, ammonium is a very, very common polyatomic cation. There's hydroxide, nitrate, all these really ones with really weird names. Now the reality is you don't have to memorize the really weird names. Let me see whether this works. We're going to find out in a second. I'm going to bring up the Google Classroom list of polyatomic ions. Now the list is actually on your Google Classroom. It's listed under ion short list. This is a list of all the polyatomic ions that you'll need to know how to use. Now, will you have to memorize them? No, that would be wasteful. But you do need to be able to find them on this table and find what their names are. So if for some reason you saw the letters CN as part of what would be a polyatomic ion, you would know the name of that as cyanide. And vice versa, if you were given the name chromate, you would know the formula would be CrO4 with a total of a -2 charge. You need to be able to use this table. Now, again, that does not mean you memorize it. That would be quite wasteful. So let's get back to the table. So how do we use this? So first question says, it's pretty simple, predict the formula of the ion formed when barium reacts with iodine. Barium reacts with iodine. So the first thing you need to do is think about the periodic table that I showed you a little bit ago and recall that barium is in column 2 or group 2, and the alkaline earth metals all form a +2 charge. And then recall that iodine is in group 17 or 7A, and those are the halogens, and they all form a -1 charge. So when trying to figure this out, you're going to say, well, wait a second, barium is going to be a +2, iodine is going to be a -1. So I'm going to need, in order to have that electrical neutrality, I'm going to need 2 of the -1s to balance my 1 barium. So it's going to be BaI2. Now, when I said you had to use the concept of crisscross, what I mean there is you're going to take barium, and again, this is just repeating what's up top, with a +2 charge, and iodine with a -1 charge, and you're going to crisscross. You're going to bring this 2 down to here, and you're going to bring this 1, the invisible 1 there, in order to balance it. That's your crisscross. When you drag the 2 from the top of the cation and make it the subscript of the anion, and you take the 1 that's on the anion, the negative charge, and bring it over. Now, you don't drag over the sign, just the value. So when writing compounds, you need to know what the charges are, and you need to know the symbols, and you need to be able to do it crisscross. So let's try a few. So if I were to do a combination of iron 2 and phosphorus, which is -3, I would do iron with a +2, phosphorus with a -3, crisscross, bring the 3 over, bring the 2 over, and this is the formula for the compound that's formed when iron ionically bonds to phosphorus. Let's try one with a polyatomic ion. So aluminum is Al with a +3, and hydroxide is an OH, an O and an H that stay together that have a total of a -1 charge. Well, I like to do this. I like to put a parentheses around the polyatomic ions to remind me it stays together. And then I'll put the -1 on the outside. That just reminds me that O and the H have to stay together. So now the 3 goes to the OH, but now I got parentheses there, so the 3 goes on the outside. And the 1 comes down here, and you get the invisible 1. So it becomes AlOH parentheses 3. Let's try this one down here. It has both of them are polyatomic ions. So I got NH4 and the polyatomic. So I'm just, for the sake of argument, going to go ahead and throw the parentheses around it. You don't have to. You're going to see in a second. Sometimes you need it, sometimes you don't. But I like to make sure to think about it as being all together. And then you have sulfate. SO4, and that altogether has a -2 charge. Going to do the crisscross, take the 2, pull it down, take the 1, the invisible 1, bring it down here. So this would be an appropriate formula. Now, obviously, these parentheses here are useless because you didn't really put a number on the outside. So more common way to see this formula written would be CH4, 2, and then SO4, -2. Now, I will tell you for the homeworks on the owls and such, you're not going to often have the charges up top. So this would just become Fe3P2, or this would just become AlOH3, or this would just become NH4 parentheses 2 SO4 without the charges. I happen to, if you were in my classroom and we were doing this on paper, I would ask you to put the charges on there because I like to make sure you realize that they do have charges, and it reminds you to go ahead and do the crisscross. Okay, so that's the ionic formula writing. How about talking about how to name these things? Well, when naming these, again, if you remember from Chem 1, there's a system to it. So with naming these, what you're going to do is essentially name the cation and then name the anion. You're going to name the cation and then name the anion. The monatomic cations, just take the name of the metal: sodium, potassium, magnesium, rubidium, scandium, whatever. However, if they're one of those ones that were in the transition stage, the various stage, I'm going to go back to it. If they're in one of these guys here, one of these ones are in the gray area, okay? If they're one of the ones that are in the gray area, then you have to use a Roman numeral. You have to put a Roman numeral after the name of the ion. So it'd become like iron is in the middle. So it's like, which iron are you talking about? Oh, I'm talking about iron with +2. It becomes iron Roman numeral 2. Or if it's iron with a +3 charge, it'd be iron Roman numeral 3. The Roman numeral tells you the charge. The Roman numeral tells you what the charge is. For the monatomic anions, again, you're going to have some choices. Those are going to end a little weird. They're going to have IDE endings. So like for oxygen becomes oxide, sulfur becomes sulfide, blah, blah, blah. And all the polyatomics have special names, but you have a chart that's going to help you figure that out. So what about those monatomic anions? Well, fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide, oxygen becomes oxide, sulfur becomes sulfide, selenium becomes selenide, nitrogen becomes nitride, phosphorus becomes phosphide, carbon becomes carbide, and on those rare exceptions, when hydrogen actually forms a -1 charge ion, it is going to be hydride. Okay, now I said that the polyatomic ions, you just take the names straight off of the chart, and that's true. So you're going to take them straight off the chart. You're not going to think about what should that number be. You're going to take it straight off the chart. However, there's a little bit of a system there that's not really recognizable. One of the things you'll notice is a lot of the polyatomic ions have either ATE or ITE endings. A lot of the polyatomic ions either end in ITE or ATE. So let's see if I can go back to that table. There it is. So I'm going to go back to this. There's a table. Look at all these anions. Acetate, now, azides of exception, bromate, chlorate, chlorate, chlorite, chlorite, cyanide, exception, hydride. We already mentioned the hydride weirdo. Carbonate, carbonate, sulfate. So you see that there's a lot of them end in ate or ite, and a lot of the ones that end in ate or ite are ones that are called, again, they're referred to as oxyanions because they're some non-metal attached to or covalently bonded to an oxygen. So let me go back to where we were. For the oxyanions, there's a pattern, okay? Whichever combination of the non-metal with oxygen that is most abundant, the combination that's most abundant gets the ATE ending. Okay, whichever one of the ions. So for instance, with nitrate, it's NO3. With chlorate, it's ClO3. With sulfate, it's SO4. With phosphate, it's PO4. So whichever one is most abundant in nature gets the ATE ending, which was a little more consistent and just simply said the 3 always gets the 8, but it's not. It's whichever one's most abundant. And then the ite ending will get 1 smaller. Now, except in situations where there's ones that have more than just the 2, if it has 1 more oxygen than the chlorate, then it's going to be per. And then if it's got 1 less oxygen than the ite, it's going to be hypoite. So here's examples. 2 most common examples are the chlorates and the sulfates. There's chlorate and chlorite, ClO3 and ClO2, but ClO4 is perchlorate, and ClO1 with just 1 single oxygen is hypochlorite. Fun fact, that's the active ingredient in bleach. Okay. For the sulfates, there's SO4 with a -2 charge is sulfate, SO3 with a -2 charge is sulfite. SO5 with a -2 charge is persulfate, and SO2 with -2 charge is hyposulfite. Notice the charges are the same. All that's different is the number of ions, ions. So when naming them, what you're going to do is simply write the names of the 2 parts. What's the name of the first part? What's the name of the second part? And sometimes you got to figure out, well, what in the heck is the charge on that various component? So let's look at some examples. So calcium is Ca. Oops. And calcium is not one that has more than 1 charge. So we don't have to worry about what the Roman numeral or anything, because it just has 1 charge. It's in column 2. It only has 1. And then you look up the Cl. Well, it's a monoatomic, and Cl becomes chloride. So that compound's name is calcium chloride. Now, next one, gallium. Ga is gallium. Gallium also is in column 3, so it does not have multiple possible charges, so you don't have to worry about a Roman numeral for that. And then there's SO4. Well, I'm just going to look that up off the table, and when I look it up, we saw that a few seconds ago, that's sulfate. So the name of this compound is gallium sulfate. Okay. Next, Ni. Ni is nickel. And nickel is one that has multiple valence states. So we got to figure out what the charge is. So I'm just put parentheses to remind me to go ahead and do that. And then I'm going to look at the OH. OH, I look it up, it's called hydroxide. Now, how do I figure out what the charge is on that nickel? Well, you got to do a little bit of math. Hydroxide has a -1 charge. So with hydroxide having a -1 charge, I have 2 times -1, or a total of 2 minuses. That means I need to have a total of 2 pluses. There's only 1 nitrogen atom, so that 1 nitrogen atom has a +2 charge. So this becomes nickel 2 hydroxide. Okay, let's try the last one. Pb is lead. And lead is one of those that have multiple charges, multiple valencies. So I'm going to put parentheses there, figure out what that is. Then I'm going to look up what CO3 is. CO3 is carbonate. Okay, carbonate, when I look it up, it's a -2 charge. So let's do my little bit of math. I have 2 times -2 for a total of -4. I need this to be electrically neutral, so I need a +4. There's only 1 atom, so I'm going to divide that by 1. Ooh, what did I do there? Oh, there's a little thing showed up at the bottom of the screen. Okay, so I'm going to divide by, come on, let me get the pen work again. Why? Okay, I got to go back to this. Yeah. So now I'm going to divide that by 1. So lead has a +4 charge. So it becomes lead 4. IV is 4. So that's lead. The name of the compound is lead 4 carbonate. So the process of naming ionic compounds, name the cation, name the anion. Sometimes the cation needs to have a Roman numeral if it's in a various stage. Okay, we're going to stop at that point for part 1. So part 1 talks about ionic formula writing and ionic naming. Part 2, we're going to deal with covalent formula writing and naming and that special ionic compound that definitely takes a little bit more thinking, of the acids. So until next time, stay safe. Um, Try to make the best of this situation we're all in. I appreciate all of your patience in having to watch videos and the like, and I'll see you in classroom. Doodles.